Hello, my name is Erin McCormic, and this is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. I will be presenting our talk, Analyzing Variability in Instance-Based Learning Model Predictions Using Recurrence Quantification Analysis. This is a project with Leslie Blaha and Cody Gonzalez. Some of you may be familiar with Anscombe's quartet. These are 4 equally sized data sets that appear similar on multiple summary statistics. Anscombe deliberately created these data to demonstrate how summary statistics can obscure important patterns in the actual data. If we assume these data sets were similar because of their summary statistics, we might miss some of the true systematic patterns seen here. Recently, my co-authors and I faced a conceptually similar issue. We took human choice data that is traditionally described in summary and reanalyzed it with a novel visual analytic approach called Recurrence Quantification Analysis, or RQA. Recurrence quantification analysis revealed that participants who had similar summary statistics still had systematically distinguishable choice patterns at the individual level. For us, this raised the question of whether model parameters chosen using summary or aggregate measures do, in fact, capture the systematic patterns we see when we study choice behavior at the individual level. Or are these model parameterizations fitting to an average participant who doesn't actually exist in the data? This question is especially important given the existing and emerging work that seeks to use computational models of cognition for effective real-time prediction, such as in the domain of human and machine teaming, and in personalized learning applications. Thus, in this project, we use recurrence quantification analysis to compare the variation in model predictions to the actual variations seen in human data. The human data that we analyze here comes from one experimental condition of a previous study on dynamic decision-making. In the experimental task, participants chose between 2 options for each of 100 trials. They chose between a stationary option with a certain outcome of 200 points and a non-stationary option with a changing probability of receiving 0 points or 500 points. The probability changed such that the value of the stationary option was higher than the expected value of the non-stationary option for the first half of the trials, shown in this lower right figure. Then, the expected value of the non-stationary option became higher than the value of the stationary option for the second half of the trials. Participants were compensated for the amount of points they accumulated in the task, so they were incentivized to choose the option with the higher expected value, which required that participants adapted to the changes in expected value. To model this dynamic decision-making task, we use the instance-based learning model of binary choice. This is a memory-based model developed from instance-based learning theory, where decision-makers value the available choice options based on observed outcomes of past choices. The processes by which past choices are retrieved from memory and evaluated in the current decision are based on the mechanisms of memory proposed by the ACT-R cognitive architecture. To summarize it, the IBL model has 3 mechanisms: the activation level of instances in memory, the probability of retrieving instances from memory, and a blended value for each choice option based on the outcome values of the instances that were successfully retrieved from memory. Decision-makers choose the option with the higher blended value. This model includes 2 important assumptions. First, that the probability of retrieving a particular instance is noisy, and second, that this probability decays with time. These 2 assumptions highlight the 2 free parameters in the IBL model of binary choice, the noise parameter and the decay parameter. The technical details of the model are provided on this slide, so feel free to pause the video to review them. We analyze 2 parameterizations of the IBL model. The first we call IBLD because it uses the default noise and decay parameters for the ACT-R cognitive architecture. The second we call IBLA because the noise and decay parameters come from fitting to the aggregate human data. We conducted a grid search to identify the noise and decay parameter pairs that minimize the root mean squared error across all 58 human participants. Both parameterizations were used to simulate choice sequences, and then analyze how variation in the model predictions compared to variation in the human choice sequences. To give you a quick sense for the basic performance of these 2 parameterizations, let's look at the predicted and actual proportion of non-stationary choices, a common aggregate measure for this data. As a reminder, for each trial, participants chose either the stationary or non-stationary choice. So here we've averaged the proportion of non-stationary choices for the 58 participants and for 1,000 simulated choice sequences from both IBLD and IBLA. The human data starts off with a roughly even chance of choosing the non-stationary choice. Then quickly the proportion of non-stationary choices drop, reflecting its lower expected value in the first half of the trials. Then, only slowly, do participants increase the proportion of non-stationary choices, as its expected value increases in the second half of the trials. This behavior isn't optimal and reflects previous observations that participants are slow to adapt to the expected value change in this dynamic task. For the models, the IBLD parameterization predicts a lower proportion of non-stationary choices than both the human data and IBLA for most of the 100 trials. But IBLD does reflect the slow increase in non-stationary choices. IBLA appears to fit to the human data quite nicely, even though it slightly underestimates the human preference for the stationary option in the early trials. With this aggregate data in mind, let's discuss how we will use RQA to assess choice behavior at the level of the individual sequences. Recurrence quantification analysis, or RQA, was developed in physics to study time series data for complex systems. It has seen limited use in psychological and behavioral research, at least so far. RQA tracks recurrence in an ordered sequence of events. Recurrence, meaning whether a particular event state repeats in the sequence. The equation at top left calculates recurrence for a set of discrete event states, in this case, participant choices. If we calculate R for every pairwise combination of trials in a given choice sequence, we can visualize recurrence in that sequence. The top right figure shows an example recurrence plot for choices in a two-alternative forced choice task with 100 trials. A black point in the plot indicates recurrence and a white point non-recurrence. When looking at recurrence plots, there are 4 features of interest shown in the bottom figure. These features are recurrence points, diagonal lines, vertical lines, and blocks of recurrence. So first, as mentioned, points indicate recurrence trials in the overall sequence where a choice was the same as on another trial. Second, diagonal lines indicate repeating sequences of choices within the overall sequence. Note that the main diagonal, called the line of incidence or line of identity, is typically removed when we compare a sequence to itself, which is the process of auto-recurrence quantification analysis. Our third feature of interest are vertical or horizontal lines that indicate sequences of the exact same choice, the exact same state, over multiple trials. Thus, fourth, a block of recurrence points visually emphasizes a series of trials where the same choice was made repeatedly. Our analysis started with a simple set of possible event states. For a given trial, was a stationary or non-stationary option chosen? We conducted RQA with the CRQA package using the additional parameters shown here, and then visualized the results with ggplot2. We also typically add one more visual feature to recurrence plots for ease of analysis. We encode the exact event state using color. Here, light green indicates recurrence of a stationary choice, and dark green recurrence of a non-stationary choice. The left figure is once again the change in the expected value of the two options. The middle figure is the recurrence plot for an optimal choice sequence, preferring the stationary option first, then switching to the non-stationary option. On the right, you can see our example recurrence plot with the stationary, non-stationary choices encoded with color. There is a light and dark green pattern characteristic of general adaptation to the change in expected value. We can also see that this decision maker had a few early choices of the non-stationary option, before a large block of choosing the stationary option consecutively. Around trial 30, this decision maker started switching between the stationary and non-stationary option. Finally, around trial 80, this decision maker settled into choosing the non-stationary option consecutively until the end of the trials. We can now turn to the first 18 participants and simulations from each of the 3 datasets. One thing to notice in these quick samples is how the frequency of switches between choice options differs in the 3 datasets. In the human data, we have a mix of participants. First, those who primarily engage in consecutively repeated choices over long periods. And second, those who primarily switch back and forth between the 2 choice options in the short term. Both approaches can show adaptation or lack thereof. In comparison, the IBLD samples here, in the middle, show more sequences with those long streaks of repeated choices and fewer sequences with the high frequency of switches seen among the human data. The IBLA samples show a contrasting pattern, where more of the sequences have a higher frequency of switches than seen among the human data. These are just 18 recurrence plots, however, so instead of making the plots smaller in order to look at even more of them all at once, we're going to make use of RQA statistics in order to view information about the larger set of simulations. Out of many possible RQA statistics, 2 of interest are recurrence rate and laminarity. The recurrence rate is the proportion of points that are recurrent out of all possible points in a recurrence plot. For a 2-alternative forced choice task with 100 choice trials, we can see a recurrence rate as low as approximately 50 if half the trials are stationary choices and half the trials are non-stationary choices. We can see a recurrence rate as high as approximately 100 if a single choice is made on all trials. We say approximate here because the line of incidence is removed. Laminarity is also a useful statistic because it indicates what proportion of recurrent points are part of a vertical line. A greater proportion of recurrent points in vertical lines gives us an indicator of more consecutively repeated choices. Thus, laminarity addresses the question about frequency of choice switching that came up when looking at the recurrence plots. So, here are the distributions of recurrence rate and laminarity in all three samples. We see evidence that the patterns suggested in those recurrence plots appear again and might be more than an artifact of just looking at the first 18 sequences. These distributions show qualitatively different shapes between the samples. Neither model parameterization exactly matches the human data in the distribution of these RQA statistics, but we can see what parts of human variation are and are not captured by the models. Let's look specifically at recurrence rate. The top figure is a repeat from the previous slide, but also has vertical lines indicating the recurrence rates for the sample recurrence plots below. I included these recurrence plots to help clarify what the different recurrence rates could look like. So, at the minimum of the range, approximately 50, we see that choice sequences all have about 50% white space or non-recurrence. But how that white space is distributed varies between participants who are better at adapting to their changing options, and the participants who switch very frequently but not necessarily optimally for the task. On the higher end of the recurrence rate range, we can see participants and model simulations that both chose the same choice option throughout most or all of the 100 trials, even though that precluded adaptation to the task. Comparing the three samples, the human data and the IBLD simulations both appear to have a bimodal distribution of recurrence rate as they stretch across the entire range of possible recurrence rate values. The IBLA simulations have some spikes contributing to its skew, but it does not fully capture the higher end of the recurrence rate range, instead predicting that most choice sequences are closer to a recurrence rate of 50. We can also note that the two local maxima for the human data and the IBLD data are opposite in their prominence. IBLD predicts more choice sequences with a high recurrence rate, and the human data shows more participants who had choice sequences with lower recurrence rate, but a notable minority did have higher recurrence rates. For laminarity, we have a similar layout of plots, the original density plot and the sample recurrence plot at different values of laminarity. Remember that laminarity is the proportion of recurrent points that fall in a vertical line. Thus, more consecutive repeated choices lead to a higher laminarity statistic. So while recurrence rate started to give us a sense for the frequency of switches between choices, laminarity tracks it even more directly. We can see that the 92.7 laminarity example in the middle of the top row of the recurrence plots is an IBLD predicted choice sequence that is relatively optimal for the task, and that it also has multiple blocks of consecutively repeated choices. In comparison, a lower laminarity value, 56, the first plot on the left in the upper row, shows a lot of frequent switching, even as we can see an average preference that trends towards adaptation to the task. Considering the distributions, we can see that IBLD predicts more choice sequences with high laminarity compared to the human data. IBLA predicts more choices with around 75 to 80 laminarity than the human data. The human data suggests most of the participants have choice sequences on the higher end of laminarity, but does cover almost the whole range, reflecting the patterns we saw in the subset of recurrence plots several slides back. In summary, we use recurrence quantification analysis to visually explore whether the variation predicted in individual choice sequences was comparable to the actual variation in human data. We found that neither of the two model parameterizations we investigated exactly matched the distribution of RQA stats seen in the human data, despite IBLA's good performance at the aggregate level of prediction. Specifically, we saw IBLA parameters predicting more decision makers with more frequent trial-to-trial switches than in human data, and IBLD parameters predicted more decision makers with less frequent trial-to-trial switches than in human data. In conclusion, recurrence quantification analysis allows us to examine the dynamic patterns of choice typically obscured by aggregate choice sequences. The aggregate fit IBL model captured the average choice behavior, but not the variation in human choices. Specifically, it did not predict the full range of choice switching patterns, which has implications for how to model concepts such as exploration behavior and dynamic tasks. We see our results here as spurring more new work. First, IBL models have been fit to individual data, with the distribution of parameters taken from these individual fits produce the variability seen in human choices. Second, are there other noise decay pairs in the parameter space with better fitting RQA statistics? And finally, what are the roles of noise and decay for predicting the variability of human behavior? Feel free to pause the video for these additional slides, but otherwise, thank you for your attention and have a wonderful rest of the virtual conference.